In today's lecture, we're going to continue our look at section 3. We've been working our way through functions of two or more variables. And the motivation, remember, is, well, we're looking at vector calculus and calculus of functions of several variables. We're extending the ideas from first year to higher dimensions. Some of this will be familiar to you, some of the sections, because they do sort of build on what you saw in 1, 2, 3, 1 in first year. So this sort of thing, this sort of thing. Today we're going to look at the chain rule and differentiability. Now, differentiability is very subtle, and it's my experience and understanding that students struggle with differentiability for functions of two variables. We'll talk about this in greater detail a bit later in the course, but today's just a little taster. So you may think, oh, I know what differentiability is. It's just when the derivative exists. No, not for functions of two variables. Not necessarily. Okay? We need to widen our understanding or our definition of differentiability. We'll look at that. And differentiability, you might think, why have I got the chain rule and differentiability together? Well, the chain rule relies on this concept. Okay? In first year, we just taught you the chain rule. Just differentiate this, differentiate that. You know? Now it's time to actually look at it in a little bit more detail. All right, so we are going to suitably define the concept of differentiability for functions of two variables and explore some of the consequences, i.e. the chain rule in this case. Now, in first year, let's just think about what the concept of differentiability was defined to be. Well, essentially, suppose I've got a function of one variable. When we say that function is differentiable at a point x0, we mean that this limit exists. Okay, if you want to write this limit another way, you might have seen it like this. Now remember, when we say a limit exists, it's just a finite real number in this case. Okay, it's not positive infinity or negative infinity. Now we denote the value of that limit by f prime of x0. Okay, it's just a value, just a number. Now, let's get slightly more technical. When we say a function of one variable is differentiable at, say, an interior point of the domain, this is what we really mean. We mean there's a unique affine function, in this case I've denoted it by A, that suitably approximates the function near the point of interest. Now, can anybody think what might that affine function be for functions of one variable, just geometrically speaking? It's not a trick question. Who said that? The tangent line, right. It turns out that this affine function is just the tangent line. Okay, so it sort of agrees with what you already know. Okay, so here, for functions of one variable, this is what we mean by an affine function. Right? You've got a linear part and a constant part, and they're added together. Okay, so ax plus b. A is multiplying with x, that's the linear part. B is just the extra constant part. You add them together, you get an affine function, what's called an affine function. So a linear function plus a constant. Now, like you said before, the graph of A is just the tangent line. So this is our affine function here. Again, think of this L as some sort of linear function. So you've got a constant plus a linear function. And in the case of functions of one variable, L is just represents multiplication by a number. Now, when we go up to higher dimensions, as you'll see today, that L is still a linear function and it still represents multiplication, but today it'll represent the dot product. You've got a vector being dotted with another vector. So that's a natural extension. If we go up even to higher dimensions, that L will represent a matrix multiplication with a vector. Okay? So the format of the underlined stuff down the bottom doesn't really change. You just need to think of it as special forms of multiplication with that linear function L. Okay, that's as simple as I can make it, really. You're just multiplying. Just think of L as multiplying with something in a suitable way. All right, so the question is, what do we mean when we say this affine function suitably approximates f near the point of interest? That's a bit loose. What do we mean by suitably approximates? I'm glad you asked. Let's discuss that for a bit. Okay, two things in our definition, I guess, well, in our understanding of this. We mean the value of the function and the value of the affine function are the same at the point of interest. So you get an exact approximation at the point of interest. And secondly, f minus the affine function approaches 0 faster than x approaches the point of interest x naught. So what do we mean by that? Well, this, or actually more suitable for our sort of setup is this. But when we come down to proving things using the idea of differentiability to prove things, actually, this is the best. This is the kind of format that is used, for example, when you want to prove the chain rule. Okay, so that starred line or two is actually probably the most important from a practical point of view. Okay, that's something you can use. Now you might have absolute values here around your x minus x naught. I just changed them to curly brackets. It doesn't really matter if it's absolute value or curly brackets. I'm just trying to keep it as simple as I can. Now, this kind of approximation is known as first degree or linear approximation. Okay, very important. We're going to come back to that a little bit later, but in the lecture, if we've got time. But this is just functions of one variable. How do we extend the definition of differentiability for functions of two variables? Well, we can base it on basically the previous slide and see what we can come up with. We can use the previous slide to build a useful definition. Okay. That's a lot of underlining. It's the same process. When we say a function of two variables is differentiable at a point, x naught, y naught, we just mean that there's a unique affine function, A, that suitably approximates f near the point of interest. Now that approximation, again, is first degree approximation or linear approximation. But with functions of two variables, you have to be a bit more careful. Okay? So in this case, what's this linear operator L doing here? Well, you can think of this as again being multiplication. It turns out that dotted with x minus x naught, y minus y naught. So again, it's multiplication, but in this case, it turns out to be a special kind of dot product. And again, from a practical point of view, this is actually what you use if you ever wanted to prove something using differentiability. Say you wanted to, prove the chain rule. And we'll do that if we have time in this lecture. Now you're going to see this again later. We're going to talk about the Jacobian, which is again another kind of derivative. And in that case, the L it's like you're multiplying with matrices. Now, anybody recognise this top? If I just cover up the bottom for a bit and cover up the limit, anybody recognise the numerator? Special form maybe from first year? What is the, so the A here, the affine function, is just that plus that. Anybody know what the affine function, what was it for functions of two variables? What was the graph of the affine function? What was it? You said it. It was a tangent, right? So now we're working in functions of two variables. What do you think the graph of the affine function would be? A plane. What kind of plane? A tangent plane. Okay? So the affine function's it's not crazy, it's just a tangent plane. Okay? And you would have looked at tangent planes in 1, 2, 3, 1. So it kind of agrees with what you already know, but we're getting a bit more mature with our analysis here and really trying to understand what we mean by differentiability. So I guess we've answered this question. What do you think is the particular form of the affine function? It's a tangent plane to the surface at the point of interest, right? Now, a good independent learning exercise is this one here. Go back and show that the definition of differentiability in 3 is equivalent to the first year definition. It's good. If you can, you should sit down and do that. Just to check to see that, oh, actually, it really does agree with what I already know. Okay, so some of you may be going, hang on, Chris. This looks like a nightmare. Give me something practical. Okay, well, I did say that, yes, this is practical for proofs, but in day-to-day operations, in day-to-day maths, the following corollary is just gold. Okay? Gold. Basically, if a function of two variables has partial derivatives that are continuous throughout some open region, then the function's differentiable. Okay? Can somebody move over? Come down and have a seat. See, this is why we're changing lecture theatres. Now, just let me repeat that, because this is important, okay? This is stuff that you can use very simply, okay? If a function has continuous partials, just df dx, df dy, then the function f is differentiable. That's gold. So, for example, polynomials. Let's say I had something like this. partial derivatives, are they continuous functions? They're continuous everywhere, right? So therefore, 1 plus x squared plus y squared must be a differentiable function everywhere for all x and all y. Okay? Okay, sometimes I just, instead of differentiable, I write diffable, just to save a bit of space. So if there's only one thing you can remember from what I've said so far, this is it. Okay, this is it. Continuity of partials ensures differentiability. And once you have differentiability, you can do, as we'll see today, you can do lots of things. Yes? Not necessarily, okay? Not necessarily. If they're not continuous, yeah, I can't think of an example now to show you that, but I'll think about it. I would think that if they're not continuous, then it's not necessarily not differentiable. Okay, it's a good question. Okay, you can see by the statement of the theorem, it's an if-then statement, not a if and only if type statement. That's a really good question. Okay. So what can we do with differentiability? Well, the chain rule. Now some of you are going, oh, come on, we did this last year. Yeah, you did, but not at the depth of what we're going to do today. Okay? We've already discussed things like product rule, quotient rule, sum and difference rules for partial derivatives. What's another rule? Well, chain rule, right? Chain rule. Now, for chain rule for functions of one variable, it's pretty simple, okay? But for two or more variables, the chain rule is more profound. Can I have a show of hands? Who remembers the chain rule from last year for functions of two variables? Okay, a couple of people, right? Okay, it's easy to forget. We spend about half a lecture on it in week 1 of Math 1, 2, 3, 1. So if you've forgotten, don't worry about it. Now, the chain rule, I guess, there's two facets to the chain rule. The first question is, why does the chain rule work? And the answer is, because we deal with differentiable functions. That's one of our assumptions. And the second thing is a computational or a practical question. How do I use the chain rule? How do I remember it? There's so many different versions. And the answer is through simple diagrams. At least that works for me. I'm a pretty simple guy. So simple diagrams, and we'll look at those as we go along. Okay, first case. Suppose we've got y equals f of x with x being a function of r and s. Now, under the assumption that f and g are differentiable functions, these are the two chain rules. Now, you might think, well, why don't I just plug that into there and just differentiate? Well, sometimes you can do that, okay? Think of x here as like an intermediate variable. Okay? Ultimately, w does depend on r and s. Yes, I agree with you. But think of x as like an in-between or an intermediate variable. Okay, so a couple of things. Firstly, a little bit of notation. You can write dw dx is okay, but I'd prefer to write df dx. Okay, you're not wrong, but just from a chain rule point of view, it's probably better to write df dx. Okay, so how do I remember the chain rule? These are real simple cases, by the way. It gets really crazy in a minute. Okay? So I said draw a picture, right? So essentially all you need to do is look at the dependency on of each variable. So, okay, now this is important, right? I realise that W equals F, and F is a function of X. So I draw a little linking line. That little link shows me that F depends on X. Now, if I move over to here, X depends on two things, R and S. So what I'm going to do is make another little link, but can we find a seat? Come on. There's a few down here. Can we squeeze in? Yeah, no worries, that's okay. We're moving to a bigger theatre next week, so don't worry. Okay, so just to repeat, X depends on two things, R and S. So I'm going to make a little split and show that dependency here. Okay, now the secret in formulating the chain rule is to work your way from the top of the diagram to the bottom of the diagram. Let me show you. Just suppose, I wanted to calculate dW dr. I look at all the roads from the top to an R. There's only one. And when I go from letter to letter, I form a derivative. Okay, so let's say I wanted to do it. Okay, dW dr can go down that way. It's df dx times dx dr. Okay? Let's say I wanted to calculate dW ds. Well, I can get from the top to an s, there's only one root. When I go from letter to letter, I form a derivative. df dx times dx ds. That's as simple as I can make it. Look at all the paths leading down to the variable for which you're differentiating with respect to. When you go from letter to letter, form a derivative. That's as simple as I can make it. Okay, so let's look at this in practice, and then we'll look at some more exotic versions. Now, if I have time, I'll come back and prove this and show you how the differentiability comes into it. Yes?
Why do we put the F function in but not the G function?
I guess it's a matter of style. Okay, you can. I guess technically it would be okay to put the G there as long as you're consistent. Yeah, so it's not going to change your final answer at all, whichever letters you use. You know, X equals G or Y equals W equals F or something like that. You should go with what you feel comfortable with. Okay. Okay, so if I've got time, I'll come back and prove that and show you the power of differentiability. Let's do an example. All right, here's a function, f. We don't know what f is. All we know is that f has some sort of dependence on r and s in the following way. Now, we're assuming that f is differentiable, then show that f satisfies this PDE. Remember, a partial differential equation is just an equation involving partial derivatives. So, I'm going to, first of all, I'm going to let this be something, I could let it be x, I'm just going to let it be u in this case, okay? So let u, sorry. Now, just to remind myself of the chain rule, you won't get the chain rule in the class in your exams, by the way, so you need to be able to come up with it. All right, so W depends on U. U depends on R and S. So we want to calculate df dr and df ds. Okay, so df dr, let's go down. It's going to be df du times du dr. Now, if you use that, du dr is going to be what? 2r? I don't know what f is, so I can't calculate df du. Who knows what f is? All we know is that it's differentiable. Let's work out the other derivative, df ds. So there's one way from getting to the top to s, df du times du ds. All right, now you use r squared plus s squared, so differentiate that partially with respect to s, and we'll get the following. Okay, so what I want to do now is take that information and show that the start equation holds. So the left-hand side of star is just this. Now remember, the subscripts mean partial derivatives. So, f sub r means df dr. So let's take what we've got and multiply. Okay, if we look at that, we've got the same thing. So we've got our left-hand side and right-hand side equal. Thus, our f must satisfy our partial differential equation star. That's a pretty simple example. That's pretty low on the difficulty scale. Okay? For something a little bit more challenging, have a look at this PDE. This is a special equation called the wave equation. Okay, it's used in physics and applied math and modelling. A is a constant. Show that the particular general form down the bottom satisfies the underlying PDE. Now, what makes this difficult is you have to take second order derivatives, and you have to, you calculate the first order derivatives using the chain rule, and then you've got to calculate the second order derivatives using the chain rule. That's a little bit more subtle. Okay, you may be able to just write down the answer. That's great, but it's a little bit harder. Okay, next step up. Here I've got f depending on two variables. So f is a function of two variables, and each of those variables is a function of one variable, t. So how does the diagram work for this? Well, here's all you can see from here, in this theorem, we're assuming f has continuous partial derivatives. So what does that mean? F's differentiable, okay? Now, let's just draw a diagram. F depends on two things, x and y. And x depends on one variable, t, and y depends on one variable, t. So, you can see there's two paths on that diagram from the top to a t. So that means our chain rule is going to have two parts to it as well. All right, so let's look at it. I can go down this path, or the left-hand path, or I can go down the right-hand path. When I move from letter to letter, I form a derivative. So df dx times dx dt. Plus the other part, df dy times dy dt. Now, you may be a little bit confused saying, hang on, why have I got partial derivatives for some and ordinary derivatives for the other? Can anyone explain why do I have a straight d's here, not curly d's? Yes? Right, there's only a one variable dependence on the x and the y. Okay, good. So you need to think about, oh, is this a function of one variable, two variables, before you write down the kinds of derivatives. Now, if you wanted to be a bit sneaky here, you could say, well, hang on, Chris, if I just write down all partials, all curly Ds, I'll never be wrong. That is true. Okay, that is true. All right, let's have a look at this in action. Okay, now this example, I actually don't like this example. Okay, I think this example's not very insightful. Anybody know why? Well, let's look at it. You've got a function of two variables, x, y squared. X depends on t cos t, y cos sine t. Use the chain rule to find df dt. What's slightly suspicious about that question? Anyone know? Can we get you a seat? Is that okay? I don't want you. I can't imagine it's very comfortable there. Can we? What's your name? Tanya. Can we find Tanya a seat? Is that okay? Yeah.
Thanks.
That's all right. We're moving to a bigger lecture theatre, so yeah, we can spread out and be comfy. Why? Especially the education students in the room. What's slightly wrong with that question? Anyone? Well, that leaves me quite unsatisfied, because if I was a student, I would say, I don't need the chain rule. I can just sub that in there and differentiate it with respect to t. And any normal person would probably do that. Okay? Do you agree? Like, why would you want to use the chain rule on this when there's probably a simpler method? And the reason I don't like it is, the answer is that, because we ask you to. Okay? So I'll do it using the chain rule, but I do it sort of unwillingly. But the next example is far more insightful, because it shows it is an example where you have to use the chain rule. There's no simple method. Okay, so let's just do this and quickly move on. All right, so f depends on two things, x and y, and each of those variables depend on t. So our chain rule is, all right, df dx, hang on, df dx times dx dt plus df dy times dy dt. So now what I would do is find these four derivatives and plug them all in. So df dx is going to be squared dx dt is going to be something like minus sine t. Df dy is going to be something like 2xy, and dy dt is going to be cosine t. Now, I've got a whole mess here. I've got t's, x's, and y's. What I'm going to do is actually put these in terms of the variable with in terms of the variable that I'm differentiating with respect to. So y is sine squared t, so I'm going to get minus sine cubed t there. 2xy, well, that's going to be 2 cos sine, and I've got another cos here, so I'll get cos squared t sine t. Now, you can kind of see in that last line why I'm kind of uncomfortable with these questions. You're going to have to sub things in later anyway. Why not just sub them in at the beginning and then differentiate? Okay, so don't pay too much attention. Don't pay too much attention to this particular example. The next one's good though. This is where you need to use the chain rule. You don't really have a choice. Okay, so here the pressure, volume, and temperature of a mole of an ideal gas are related by the following equation. Find the rate at which the pressure is changing with respect to time at the instant where we have these particular values. Okay. So, as I've listed, we want to calculate the derivative and evaluate it at the above instant. So here, again, we can just go through and look at the dependencies. P depends on big T and V. Now, this is interesting. I'm going to claim that big T and big V depend on time, little t. Anybody know, can anyone justify why that might, why we can say that? Yes. Sorry, say again?
You've got those two last derivatives.
Yes, we've got the derivatives. We've got d big T, dt, and d big V, dt. So we can, expect that these two sort of intermediate variables depend on time. So, the chain rule. Okay, so oh, sorry, they should be partials. Okay, well, we don't know what big T is, and we don't know what big V is, but we can do some of these differentiations. Okay, I have this relationship here, so I can work out that derivative and that derivative. So if I differentiate partially with respect to T, I'll get that. If I differentiate partially with respect to V, I'll get something like this. Sorry, that's a T. Now, at our point of interest, all we really want to do is plug in these values into Okay, so 8.31, V's 100. D big T, D little t is 0.1. Big T is 300. V squared, 100 squared. D big V dt is 0.2. So all we have to do is simplify that. And according to my calcs, you should get something like that. And we don't know if time's in seconds or minutes or whatever, so I'm just going to write it in kilopascals per unit of time. Now, this is a really good example, okay? This is a really, really good example. Okay, well, we can look at slightly more exotic versions of the chain rule. So that's what we're going to do now. But the idea is just drawing a little diagram. That's what, if I want to use the chain rule, I will draw that diagram. Okay? I'll draw the diagram and work my way from the top to the bottom. Anyone still going? All right, so now we've got a function of two variables where each of the variables is a function of two variables. Okay? Again, just draw the diagram. So f depends on two things, x and y. And y depends on, x depends on two things, r and s. Y depends on two things, r and s. So all you've got to do, say to find dw, dr, find all the paths down to an r that lead to an r. When you go from letter to letter, form a derivative. That's all it is. Let's have a look at how you can use this particular version. Again, this is a really good example too. Okay, this is like, you know, maybe class test 1 type worthy. So let f have continuous partial derivatives. In other words, f's differentiable. Show that a function with this form satisfies the following PDE. So let's give it a label because I'll refer back to it a bit later. All right, so let's look at our dependence. I guess I'll let that be x and let that be y. U minus v, v minus u. Okay, so under these sort of labels, f's a function of 2 variables. A little diagram's there. Let's calculate the partial derivatives by using the chain rule. All right, so dz du, so we want to calculate that derivative and that derivative. dz du, let's find all the paths to a u. It's going to be df dx, dx du plus the other path, df dy times dy du. Oh, sorry, they should be partials, shouldn't they? Sorry. Okay. Now we don't know what f is, so we can't calculate these 2 derivatives, but we can calculate these 2 derivatives. So dx du is going to be 1. So just to save space, I'm just going to write this as f dash. Oh, hang on, no, I can't do that. I'll write it as f sub x. So dx du is 1 from up there. dy du is minus 1. Okay, what about dz dv? Well, let's check all the paths to a v. df dx times dx dv plus df dy times dy dv. So again, I'm just going to use subscripts to save a bit of time. Okay, so I can calculate that and that from here and here. So dx dv is going to be minus 1 and dy dv is going to be positive 1. So the left-hand side of our start, I know it's a bit messy, the left-hand side of our start PDE is just these 2 derivatives added together. So if you add that to that, they're going to cancel each other out. So, our general f must satisfy star. That's our conclusion. That's a good class test worthy question. Now you can keep going with the chain rule. Let's have a look at another version. Well, the next version is where you've got a function of 3 variables, and each variable depends on 1 variable. So let's have a quick look at that. Okay, so what would the picture be for this one? It'd be a split of 3. You're going to have 3 parts leading to a t, so that's where each of these 3 terms comes from. Hopefully you're getting the picture now. It doesn't matter how complicated the dependencies are, just draw a simple diagram and work your way from the top to the bottom. Easy. All right, here's an example that I've created earlier. Function of 3 variables. Each variable depends on t, one variable. So here they've calculated dw dt just by using the chain rule. So go back and apply the chain rule, and then I guess you can put it all in terms of t because you've got t equals 0. That's your point of interest. So you end up with some value. Now you can think of these intermediate values. Anybody recognise the curve associated with these? It's a helix, right? It's a helix. So again, here it is. Now, starting to get a bit crazy. Function of 3 variables. Each of those variables depends on 2 variables. Whoa. Again, just draw a picture. Right? X depends on 2 things, Y depends on 2 things, Z depends on 2 things. That's it. Okay, so here's another example based on that I've created earlier. Have a read through that. And I'm going to leave you with the following. I've actually run out of time, but I'm going to leave you with the following semi-applied problem, I guess. Here you've got a special PDE known as the advection equation. A is a constant, and U is a function of x and t. Now, you can think of x being position and t being time. And I've given a little bit of an outline into, a possibility, what U might represent. So, you're dumping salt in a river, and if the fresh water is flowing quickly, the form of transport of salt in the water would be advective. Now, again, U would represent the concentration of salt at position x at time t. I'll leave that question for you to do.